thank you for the chance to talk to you all about the Pandora mission. This is like a real treat because I almost kind of feel like you guys, most people sitting here could give half of this talk, so it's pretty cool. Anyway, so Pandora is a small sat, and the whole goal of this small sat is to really do a multi-wavelength characterization of exoplanets and their host stars. Elisa Quintana, who who gave one of the talks earlier today, is the PI, and I am lucky enough to be her deputy. Hang on. Okay. And Pandora was selected as one of the 4 missions that NASA selected to be one of their inaugural Astrophysics Pioneers program. The Pioneers program is a new line of small missions, a $20 million cap, 5-year lifetime, and part of the goal is to incorporate lots of earlier career scientists in these focused missions. And so it's a pretty cool program, although we are definitely figuring out as we go along. My first couple of slides, I think, like I said, you guys know this, but the whole point is the exoplanet transmission spectroscopy is how we learn a lot about the atmospheres of transiting planets. And it's one of the primary science cases for JWST. But of course, there's a underpinning assumption that most people have historically been using, which is that the emergent starlight is uniform. And as we know, and as has been explained so brilliantly over the last 2 days, that is not the case. And so Pandora is really designed to get into this problem and the way we're going to try to unravel this problem is to do simultaneous long time baseline visible photometry and infrared spectroscopy. So the idea is with the visible photometry, we want to get an idea of the stellar activity, and then we will compare that with the infrared spectroscopy. And our science goals are to determine the spot and faculae covering fraction of the exoplanet host stars and the impact of these active regions on the exoplanet transmission spectra, and also to identify which exoplanets are hydrogen or have hydrogen or water dominated atmospheres, and determine which types of the planets tend to be covered by clouds and hazes. And so a brief overview of the mission, our launch is planned for November 2024. We have a 12-month mission duration, and that is taking the observations and publishing our main results. So it's a very abbreviated timeline for a mission. The telescope is just shy of 0.5 meters, and our visible range is 0.3 to 0.6 microns, and our IR spectroscopy range is a sun-synchronous orbit. And over the year, we plan on observing 20 K and M dwarfs with something like 40 planets spanning everything from Earth to Jupiter sized. And our observing strategy, as I kind of said before, is really to do this visible channel where we get an idea of the activity and the star spot rotation, and the simultaneous spectroscopy to get the variations in both the stellar spectra and then during transits to back out the planetary spectra. And we plan on, our baseline is to get 10 transits for each planet and to have a 24-hour observation window around each transit, so we can really have plenty of baseline. And this is the kind of thing you can do with a small dedicated mission where you can invest a lot of time in specific sources. And this kind of long baseline is very difficult to do in a more general facility. And just to kind of show where, compare Pandora to some of the other facilities and how Pandora really fits in and complements these other facilities. So we will operate a wavelength range similar to HST's WFC3 IR band that we know and love from transit spectroscopy. And we're going to have sensitivity similar to HST, but with the addition of the observations in the simultaneous observations in the optical, and we are going to get very long baselines for all of our sources. We are going to launch after James Webb, but we'll be up at the same time as James Webb. And so we're hoping that, we can inform the James Webb observations and interpretations. And, we may adjust our target list depending on what comes out of Webb as well. Really, the bottom chart is really kind of to show that while we have all these great facilities like TESS, Hubble, James Webb, and Ariel to do that we can apply to these problems, Pandora is really the only one that lets you do the long time baseline, the IR observations, the visual observations simultaneously and at a low cost and on a timely basis. And to another thing to kind of put into context here a little bit, Nicole Colon shared this plot with Elisa and I yesterday. We were both so excited by it. We both put it in our presentations. These are the transit and eclipse exoplanet observations that are planned in JWST's early release science and GTO programs. And one thing I'd like to bring your attention to is most of these are around lower mass, cooler stars, more your K and M dwarfs. And so much of what we know about stellar activity and how the stellar activity and its effect on spectroscopy is based on the sun. And that is, super important, but understanding the sun is not going to be enough to really understand what's going on with the types of targets that James Webb is going after. And this is where Pandora comes in. Our target list is going to include a range of K and M dwarfs with a variety of rotation rates and a variety of planet sizes. This is our notional target list. It will of course change, but you have to do the sanity check that there's enough targets to actually do what you want to do. And our goal with our target list is to span this K and M dwarf range, span the range of rotations, and span the type and size of planets so that we can get an idea of how big of this effect and what we should worry about. And here's just a simulation of what our data would look like. Here is the team. As I said, Elisa is our principal investigator. I'm her deputy. Every NASA mission has a chart like this with lots of boxes, which I think NASA geeks find very interesting, but I won't necessarily bore the rest of you all with 2 minutes left. And we have a science team that I listed down at the bottom that we're really excited about. And so here's our status. We got our selection letter in January. Our funding started in February. So we are literally 5 weeks into this mission. We have 6 months to prepare a concept study report. NASA has all of these gate reviews that you have to successfully get through to continue your mission on. And our next one is the concept study report. To get through that, we've got a bunch of engineering trades that we are executing on detectors, thermal design, baffling. We're developing a notional year in the life observing plan, revising our target list. We're simulating observations of benchmark targets, and basically kind of sharpening our pencil above and beyond what we have in the proposal and putting some more meat on the bones of our plan. And then I just wanted to leave you here with, here's kind of like the Pandora mission all in one slide to just kind of summarize our goals and how we're going to go about it. And with that, thank you very much.
All right, thank you very much, Jessie. This was a great overview. I'm looking at the Slido right now. There's no questions over here, but folks can, of course, unmute themselves or post the questions right now if they want.
Yeah, hi, this is Sami Solanki. That was very interesting. A question there, will you have kind of photometric accuracy also in the infrared channel, or is that really only for the spectroscopy?
So the infrared channel is really for the spectroscopy.
So it will not be photometrically as accurate?
I'm not entirely sure I understand your question, but the goal is really to do the spectroscopy of the stellar and exoplanets with the higher channel.
The background of my question is that if you have a single visible channel, you will not be very well able to distinguish between faculae and spots. But if you could also have photometric accuracy in the infrared channel, then you might have a chance of doing that.
Right, like with HST, basically.
Yeah.
Yeah.
I saw Ben Rackham pop up. He probably has a much better answer to that question because this is his bread and butter, what he's bringing to the team.
That's essentially what we're going to try to do is use it as people have used HST's out of transit data, but with the additional leverage given by that photometric point from the visible and the longer baselines. So yes, we will be doing like a spectral analysis of the out of transit data.
Great, thank you.
All right. Thank you again, Jessie, for this excellent talk on this very exciting mission.